Good afternoon. I'm Jon Rognes, and I have the honor of introducing the speakers, welcome speakers this afternoon. So first we have Oscar Randal-Williams, who's the Sadlerian Professor of Pure Mathematics at the University of Cambridge. He was a speaker at the ICM in 2022 and a Fellow of the Royal Society last year. His title is, like the local cider, it seems innocuous at first, in the cohomology of marginalized spaces. Please.
Thank you very much for the introduction and for being interested enough in what I want to tell you. So I want to start by making some propaganda about a certain area of mathematics, which is studying cohomology of moduli spaces. But most of the talk is going to be talking about a specific recent example of doing exactly that, which has applications to number theory. It was motivated by a question in number theory. But let me start at the beginning. So moduli spaces, anything that you think is moduli space, I will allow to be included in the list of good moduli spaces. So the first and best one is the original, so Riemann's moduli space of genus G Riemann surfaces. So the points of this space are genus G Riemann surfaces, and points are nearby if you can find a map between them which is quite close to being conformal, maybe. And the closer it is, the more like a conformal map it is, and the closer they are. Sort of variant of that is you replace surfaces by graphs. So we look at rank G graphs with edges that have lengths, and you can move around this space by shrinking and expanding the lengths of edges. Maybe you shouldn't shrink a loop down to a point, so the genus of the graph should stay constant, but other than that, you're allowed to move around in the space of graphs by changing the length of the edges. Another example that might be familiar to some people is so-called moduli space of principally polarized abelian varieties. Doesn't matter if you don't know what that is. One that's closer to this talk is the space of n particles inside some other space. So this is a bit different in flavor. In the first examples, we were talking about spaces of abstract objects, where these are somehow objects inside some other thing. So they come with a sort of concrete description of subsets of some space X, which I think of as being particles, and maybe we think of them as being sort of indistinguishable particles. So they're not called 1 up to n, they're just points in the space. If I take 2 points and they swap places, that's actually, I'm back to where I started. And the last one is a kind of extension of that. You can think of n points as being a compact zero-dimensional manifold. And then you can change the number 0 to another number. So you can look at the space of submanifolds of something, let's say infinite dimensional Euclidean space, which happen to be diffeomorphic to one that you have in mind. For example, n points, or the circle, or something else. So you can make many sort of further examples of this flavor. If you have some kind of moduli space, then it's a reasonable idea to take its cohomology. Just in the sense of algebraic topology, moduli spaces parameterize some kind of mathematical object. And dth cohomology of a moduli space is exactly, basically, invariance of d-dimensional families of whatever that kind of object is. You get to pick, I guess you get to pick an abelian group A, so it's sort of A-valued invariance of d-dimensional families of whatever the thing is. So let me tell you, in the case of MG, some examples of that. So the first calculation of the cohomology moduli space is from 1882. So Felix Klein showed that the 0th cohomology of MG is integers. That means that every locally constant function on MG is globally constant, or in other words, is connected. So that means given any two genus G Riemann surfaces, so in other words, you think of them as being two complex structures maybe on the same space, you can get between them by deforming the complex structure somehow. Not quite true, but you're allowed to deform the complex structure, and then you're allowed to do a symmetry of the whole surface as well. By those two moves, you can get between any two complex structures. So that's a somehow deep theorem about surfaces. You can deform any one to any other one, but you can encode it in the sort of statement about the cohomology of this space, and then you can sort of carry on going. So quite a long time later, Mumford calculated basically that the first cohomology is 0, so there's no interesting z-valued invariance of bundles of Riemann surfaces over a circle. That's not to say that there's no interesting bundles of Riemann surfaces over a circle, which is not true, but there's no interesting z-valued additive invariance of such things. And a little bit later, John Herer proved that the second cohomology turn out to be the integers, as long as G is at least 3. And this is a very symptomatic thing of this kind of business. Very often moduli spaces come in a sequence. There was a parameter called G, here it became called N, and here it became not a number, but just a manifold that you get to pick. The index is the sequence. And it very often is the case that for small values of that parameter, there's some funny business going on, and then after some time, it settles down into some sort of systematic phenomenon. Okay, and we see that here. So the earlier values, I think, in genus 2, it turns out to be Z mod 10, and in genus 1, it's Z mod 12. But then it becomes Z after that. So many communities in mathematics are interested in modular spaces, and then by extension in their cohomology. And this is somehow a very good thing, because all these different communities have different tools that they know, and they have different points of view, and they have different applications in mind for these objects. But we are, at the end of the day, talking about the same objects. So whatever somebody proves using the tools they know, I can now use and see how it interacts with the tools that I know.
Oh, sorry, could I interrupt?
Absolutely.
What you said just now. Are you talking about the moduli stack or the space?
All of these things are welcome.
So you just said mod 12, right?
So then I mean the stack, yes. Yeah. And so the fact that these same kind of objects are studied by lots of different people with lots of different perspectives makes the subject kind of particularly interesting and rich, I think. And fairly recently at least given the scale of time, so Riemann invented his modular space in about 1850, and Klein proved it was connected about 40 years later. In the last 25 or 30 years, there's a new kind of community that's got interested in these, which is a community coming from what used to be called algebraic topology, and is now called homotopy theory. And this was started by Ulrike Tillman, this sort of connection between modular space of Riemann surfaces and homotopy theory. And she proved something which I won't emphasize very much, which is that the stable or the cohomology of MG can be calculated as the cohomology of another thing, which is called an inflow loop space. And this is just some other topological space, but it has a very completely different nature to the nature of MG. Okay? So there's no reason something like this ought to be true. And this was somehow weaponized by Madsen and Weiss to completely calculate the cohomology of MG in a certain regime. And it's sort of what I said before. You fix the cohomological degree, and then you insist that the genus is big enough compared to that cohomological degree. And in that range, there's just a complete answer for what the cohomology is. And here, all of these classes called kappa 1, 2, these were known long ago. They were due to Mumford. Somehow the new content, in some sense, is that that's all there is. There's no surprising invariance of families of Riemann surfaces that we didn't already know about before. So this new community has a kind of its own new point of view. It's sort of inspired by ideas from homotopy theory, ideas from Quillen's definition of algebraic K-theory, and things of that nature. And when these methods apply, which of course they don't always, because I'm not a messiah, but when they apply, then they tend to give very powerful results that are not really accessible any other way. So, as I said, what I want to do today is to talk you through one recent example of using this set of techniques to prove something that was independently interesting. So I want to start with the example of the moduli space of finite subsets of the plane of a given cardinality, let's say n. And these are indistinguishable points in the plane, and in particular, they're different points in the plane, so they're not allowed to be on top of each other. Okay, so to give you a set of n points in the plane which are unordered, one way to encode that is to give you a polynomial that has those roots that has those points as its roots. And when I do that, then I cannot possibly, they're not ordered, right? So that's a good way to encode the fact that they're not supposed to be ordered. So it's exactly the same to give you n points as to give a degree n monic polynomial with no repeated roots. It's exactly the same. And when we think about it that way, then it's sort of obvious how to make it into a topological space. It's just a subspace of the space of all polynomials. So this has been studied for a very long time, and the easiest sort of algebraic invariant of this space is its fundamental group, which turns out to be this famous braid group of Artin. So if I have a loop in the space of n points in the plane, that means I start with n points, they move around, and then they go back to where they were to begin with. Maybe not each point goes back to where it was to begin with, but it goes back to where maybe some other point was to begin with. And if I play out a video of such a path, going from top to bottom, of these points moving around, then it will trace out a braid. So a braid just means a load of strings going from the top to the bottom that just monotonically, they always move downwards. They're not allowed to go down and come up again. They always move downwards, but they're allowed to wind around each other and so on. And it's just a matter of language, really, that such pictures are loops in the space of configurations. And of course, it's a group because I can take two such pictures and stack them on top of each other. known as Artin's braid group. And in this kind of area, an early calculation of the cohomology of this moduli space of endpoints in the plane is due to Arnold. And the answer turns out to be surprisingly simple. So I'm going to write it with rational coefficients, otherwise it's not very simple. And the answer is, as long as you've got more than one point, the 0th cohomology is one-dimensional, and the first cohomology is one-dimensional, and that's all there is. However many points you have, as long as there's at least one. At least two, sorry. Here you also see this sort of behavior. If the configuration space of one point in the plane is, of course, the plane, and its cohomology is slightly different. It doesn't have a class when I is 1, I suppose. But once we go past some threshold, which in this case is very early, it's 2 points, then things become systematic. This is not the case study. This is a very old example. The case study builds on this example. It goes as follows. So if I have a polynomial with n roots, I can take the branch cover of the complex plane that's exactly branched, it's the double branch cover, which is exactly branched at those roots. Okay? And if you construct it explicitly, then of course you exactly write down the polynomial y squared is d of x, where d is your given polynomial. And you look at pairs of complex numbers such that y squared is d of x. So here is my attempt to make a cartoon of how you do that, of course. This has much to do with, branch cuts and things of that nature. So if I want to construct this surface, I take 2 copies of the complex plane. I pick some way of connecting the points to infinity, which I've drawn here by dotted lines. I take 2 such copies, I cut them along those dotted lines, and then I glue them in the way that's probably difficult to see on these slides, but I glue the left side to the right side and the right side to the left side along each thing. So it's impossible to draw the result of doing that, so I've just drawn the instructions for how to make it. Okay? It's probably not impossible. It's impossible for me to draw the result of doing that. And what you get is then a Riemann surface. It will be a non-compact Riemann surface, of course, and it may be missing 1 point or it may be missing 2 points, depending on how many branch points there were. If you think in your mind of doing this gluing, and you think about walking around that boundary of this surface, you will go along here, then you will come up there, then you will come down there, and you'll see that you're back to where you started. So the boundary of this has 2 components, and that's because there were 2 points in the base. And if you did the same thing with 1 point in the base, you would discover that it has 1 component on the boundary. There's some slightly annoying parity problem that you have to deal with, but this is a way of assigning to every polynomial a Riemann surface. Okay? Whose genus and whose topological invariance, like how many boundaries it has, are just known. So what I can do is I can then take any topological invariant I know of surfaces and apply it to the one that I get. In particular, I can take the first cohomology of this surface. So this is now a slightly complicated thing. I'm taking a polynomial, d, I make the branch cover that it defines, and then I take the cohomology, the first cohomology of that space. So that gives me, for every point d, so d is a point in the space of polynomials, it gives me an abelian group. But because it's the first cohomology of a surface, it has a bit more structure. It has a so-called symplectic form on it. Intersecting or taking cut product of things on the surface gives a skew symmetric form on this abelian group. So what I have is a local system of symplectic forms over the space of polynomials. That's the resulting data. And this has a name. It's called the reduced integral Burel representation. Okay? And it's, if you think about giving a local system of abelian groups over some space, it's exactly the same as giving a representation of the fundamental group of that space, telling you how to move vectors around as you go around a loop. So another way to say the same thing is that I have a homomorphism from the braid group on, let's say, 2G plus 1 strands to the symplectic group of 2G by 2G symplectic matrices. Okay? So here there are 2 cases depending on whether n is even or odd. From now onwards, let me always assume that n is odd. Okay? Otherwise, I'll have to do 2 cases of everything. So this geometric construction, you can also express in this sort of very algebraic way. I guess I should point out that the braid groups have a completely explicit presentation, which is very easy, and matrices are matrices, which are very easy. And you can write down a formula for this if you want to, by saying what each little elementary braid, what matrix it assigns. And which is just to say that you can make it a lot more explicit than it sounded, the way I've described it. For the kinds of questions I'm interested in, that seems to be of roughly no advantage to write it down explicitly like that. It's much better to think about its sort of conceptual meaning, which is the way I sort of introduced it. So you can then ask the following question. You can take the fundamental representation of SP2G, so just the Z to the 2G with its usual action of that group, and you can ask, what is the cohomology of the configuration space now with coefficients in this representation? So that I haven't introduced before, but let me say it again in a kind of conceptual way, like I tried to say what cohomology of a modular space means. A valued cohomology of a modular space was trying to get, if I have a D parameter family, is trying to get A valued invariants of such things. Cohomology, when you put a representation here, is also trying to get invariants of families of such things, except that where the invariant lives is allowed to depend on the point. The invariant's not always in the same abelian group, it's in a system of abelian groups that change depending where you are. Other than that, it's the same sort of idea. And another thing that I didn't emphasize earlier is that not only are the braid groups the fundamental group of these configuration spaces, but they're interchangeable with them. The technical term is that the configuration spaces are Eilenberg-MacLane spaces for the braid groups, which means that cohomology of these configuration spaces is exactly group cohomology of the braid groups with coefficients in a certain module as well. So again, from my point of view, the left-hand side is much more approachable than the right-hand side, but it is a purely algebraic question that you could try to answer by purely algebraic means if you thought you had an idea of how to do so. And once you've got this far, you may as well go a little bit further. I mean, the symplectic group has its fundamental representation, but it also has lots of other representations, so you may as well take any of those as well. So the irreducible representations of the symplectic group are they're indexed by partitions of length m as g. So you may as well ask the same question. Given that we're just asking questions, which is a very cheap thing to do, you may as well ask the same question for these. So let me pause for a second. There are many calculations you can pose yourself and try to answer, and they may be very difficult. And if you want to pursue this one, then you probably want to have a rather good reason for doing so, not just because you thought of it and maybe it'll be interesting, maybe it won't. And the motivation for this comes from an explicit question in arithmetic statistics that I'd like to spend the next few slides explaining, and then I'll come back to something about answering the question, okay? So the motivation for the question is the following. So now I fix a prime number q, or maybe a power of a prime number, and it should also be odd for some technical reasons. And I look at polynomials over the field with q elements, which are monic and have no repeated roots, aka square free. And let's say the degree is n is 2g plus 1, just like it was in my previous couple of slides. And then I can write down exactly the same formula that I wrote down for defining a Riemann surface, except that now x and y are elements of fq. More generally than that, they're not really elements of fq, they're elements of any ring that happens to contain fq, or the fancy way of saying it, I'm really talking about a scheme, which means I can ask what are the points of this for any ring that happens to contain fq. But apart from that small detail, I look at pairs of points that satisfy y squared is d of x, and if I evaluate this at fq, then this is some finite set. Because before I impose an equation, there's only q squared many points. And so then I ask for ones that satisfy an equation, and there's going to be slightly less than q squared many points, probably. And I can ask how many there are. And it turns out that the best way to think about this is not to ask how many there are, end of story. The best way to think about it is to ask how many there are over fq, and also how many there are over fq squared, and also how many there are over fq cubed, and so on, and assemble all of those numbers into a generating function. That's the best thing to do. So there's going to be an enormous equation in a minute, which I'm warning you about, and I will explain the equation from left to right, and it does not have to be understood all in one go, okay? So, as I said, you can count them over every finite extension of fq, And then I want to start on this side. You take the number of solutions over fq to the k. Those are just some integers. You assemble them into this kind of logarithmic generating function inside, and then you take the exponential of that. Okay? So because this number, whatever it is less than q to the 2k or something, this thing inside has a non-zero radius of convergence. And so its exponential also has a non-zero radius of convergence, and it turns out to be t less than 1 over q. Okay? So the left-hand side, at least on some region, is a holomorphic function of t. And it is the so-called Riemann zeta function associated to the curve CD. Okay? And just like the Riemann zeta function, the actual Riemann zeta function, it has a meromorphic extension to the whole complex plane. And not only do you get a meromorphic function, in this case something much more special happens, which is you get a rational function. And not only that, but we know exactly what the denominator is. So the information is just the numerator, which is a polynomial of t with integer coefficients. But what it is depends on the actual equation that you chose, of course. Okay? It varies.
What is this CD bar with a bar on top?
Okay, so there's one small thing that I was hoping not to have to talk about, which is that, so here I've described an affine curve. It's an affine curve, and I should ask this question for its projective completion. Yeah?
Why is it natural?
Okay, let me now confess, I've no idea. This is not my day-to-day business. This is me trying to explain why people do this. So I don't know.
Maybe one short answer is that if you write it as an infinite product, it becomes the exact analog of the Riemann zeta.
Very good. So this has other properties similar to the zeta function. It has a functional equation, and it has a critical line, which is a symmetry axis, if you like, of the functional equation. And the critical line turns out to be somehow q to the minus 1/2. And what's especially interesting then is the values. You know, this numerator can be different things depending on what the actual polynomial d was, but what's particularly interesting is the values of that at the critical line, which is actually a critical point, q to the minus 1/2. And so there's a conjecture about this due to Connery, Farmer, Keating, Rubinstein, and Snaith. And it's again kind of big, and I'll explain it step by step. So I fix q, which is my prime power, and I fix a number r. And I ask about the moments of these special values of this function. Okay, there's some normalization at the beginning, which is not very important, but I take the sum over all monic square-free polynomials of degree 2g plus 1. I evaluate this numerator at the special value q to the minus 1/2, and I take its rth power. Okay, so this is the rth, ignoring the normalization, it's the rth moment of the values of this function that assigns to d p c d of q to the minus 1/2. And they have guess for what this is supposed to be. It's supposed to be an explicit polynomial of degree something applied to 2g plus 1, plus terms that are little o of 1 with respect to g. Okay, so here importantly, q and r are fixed, and g, which is roughly the degree of the polynomial, is sort of large. Okay? So this is called conjecture star because it's not really their conjecture. Their real conjecture is a conjecture about number fields because they're actually number theorists. But there's a sort of game you can play is that whenever you have a reasonable standard thing about number fields, you can ask the same thing about function fields. And this is the analog of their conjecture translated from the case of number fields to the case of function fields. Okay? So, right. So this obviously has some superficial similarities, like this thing up here, if I formally take x and y to be complex numbers, is this Riemann surface that I wrote down a minute ago, to the extent that that makes sense. And when does that make sense? Well, I mean, I can't ask about the complex solutions of a polynomial over fq, so that doesn't make sense. But if I had a polynomial of the integers, I could do two things. I could ask about its complex solutions, but I could also reduce it mod p or mod q and ask about its solutions of fq. So the reasonable way to compare the two things I've said is if you had something over the integers. Then you could complexify it, but you could also reduce it mod q. And there's an incredible relationship that happens in this situation. So when you have what's called a scheme, which just means a load of polynomials defined over the integers, then you can do both things. You can ask how many solutions they have over fq, or over fq to the k, maybe. Or you can ask about the complex solutions, which is a topological space, and you can ask about its cohomology. And similarly, if you want to count points, not just count how many there are, but maybe you want to have some weight function assigned to them, then that turns out to translate to cohomology of this space with certain local systems on it, where the local system is some encoding of the weight function that you chose on that side. And this relationship uses all sorts of incredible pieces of algebraic geometry from the 60s and 70s, so the so-called Grothendieck-Lefschetz trace formula, the comparison theorem between étale cohomology and ordinary topologist cohomology, and a theorem due to Deligne, which bounds so-called Frobenius eigenvalues. Let me just tell you what it looks like in a kind of example. It tends to say things of this form. The number of solutions over fq is some normalization times the alternating sum of the traces of a certain operator called Frobenius, acting on, the way I've written it, the étale homology of x. All these, so that this, I guess, is the Grothendieck-Lefschetz trace formula. The comparison theorem tells you that you can swap this étale homology for just ordinary homology under certain conditions on x. And so that gets you a little closer to topology. What it doesn't tell you how to do is say anything about this linear map called Frobenius. And that's where this next ingredient comes in, this bound on Frobenius eigenvalues, which is that the eigenvalues cannot be any old thing. There's a certain formula that the absolute values have to satisfy. And that means that if you want to maybe not calculate completely, but estimate this side, then if you know something about the eigenvalues, then it's not such a bad estimate to just know something about the dimensions of the spaces involved. So, okay, that won't give you exact calculations, but it will give you some sort of estimates. And you can try to make more heuristic estimates by saying, well, maybe the eigenvalues, okay, the absolute value is a certain thing. Maybe we believe they're equidistributed among possible such things, and that will give you, I mean, that's not true, but that will let you make other sort of heuristic guesses coming from this, even though you don't know anything about this linear map. So let me just say how this looks in the one example I've talked about. So I can look at, I've written it in sort of scheme language, so configurations of endpoints in A1, the line. So its cohomology of its complex points is what I told you Arnold calculated. It's Q in degrees 0 and 1. And if you stick that in this recipe, you discover that the exact number of degree n monic polynomials with no repeated roots is Q to the n minus Q to the n minus 1. So in this case, you can actually calculate what the Frobenius map is, so you get an exact answer. Okay? Maybe another way to think about this is to divide by Q to the n. And then the left-hand side is the density of polynomials with no repeated roots among all polynomials. And it says the density is precisely 1 minus Q inverse. And this is a little special in that the dependence on the n is incredibly modest. I didn't have to write plus little o of something to do with n because I just had an explicit answer. But that's a sort of the shape of this technique when it works. So a couple of years ago, Bergstrom, Diacono, Peterson, and Westerland used exactly this technique, applied to basically this configuration. There's a small variant here that is not very important, basically to configurations of 2g plus 1 points in the affine line, and with a certain local coefficient system, which is the following. You take this fundamental representation that I mentioned, this Bureau representation, you take its full exterior algebra, which you forget is an algebra, you just add up all the exterior powers, and then you take the rth tensor power of the whole thing. Some enormous vector space. But it's invented so that when you do the corresponding weight count, you exactly get the left-hand side in this conjecture of Conry, Farmer, Keating, Wittgenstein, and Snaith. That's how you cook it up so that it will do that. So this is some enormous representation of the symplectic group. We know representation of the symplectic group completely, that we know they're irreducibles, they're indexed by partitions of length at most g, and you can do the calculation of how it splits into irreducibles. Some enormous exercise in symmetric function theory and things of that flavor. And you get the multiplicities turn out to be certain polynomials in 2g plus 1, that they are what they are. They turn out to have degree exactly r times r plus 1 over 2. And using this, these authors show that, well, they completely calculate the cohomology as g goes to infinity. And what I mean by that is that the limit as g goes to infinity, not some large g anything, like the actual limiting thing. They completely compute it, and when you combine that with these polynomials, you exactly get the right-hand side in this conjecture. You remember the conjecture? It would be a few slides back. Let me maybe go back briefly. The shape of the conjecture was some polynomial of 2g plus 1 of degree this. And the claim is when you add up all those polynomials with certain multiplicities that I said on the next slide, you get exactly the one. So this is an explicit polynomial that there's a formula for, and you get exactly that explicit polynomial. And so that's one thing that they do. And they also show that the conjecture would follow for fixed R and all big enough Q if one also knew that these cohomology groups didn't change as you increased G.
This is using your relating the C cohomology to C points with what happens.
It uses, yeah, right, it does, I guess the first part, it does a calculation in topology, and then the sentence showing that it recovers the right-hand side of the conjecture is applying the Schrödinger left machine, yes. So they also show that you want to replace the sort of G equals infinity answer with the G equals G answer, because that's what you're actually interested in. And they show that the conjecture would follow for fixed R and all big enough G if one knew that the cohomology stabilized with G. And let me emphasize this because this is very important. You need to know a formula like this. The ith cohomology is independent of G in a range I less than, so it doesn't matter what the linear function is, some linear function of G, okay? But you need to know it for all lambda with the same A and B, okay? I emphasize this because this is going to be my little contribution. So before that, let me talk a little bit about how they do this and what this, I've sort of asserted several times there's some new homotopical ideas that are good for doing something or other, and I haven't really said anything about what they are. So it tends to exploit locality in a very useful way. So configurations of endpoints in the plane is one path component of configurations of finitely many points in the plane, where you don't say what the finite number is. And I can sort of test, if I give a subset of a plane, and I want to know is it a configuration of finitely many points, then what can I do? I can look locally, and within each ball I should see probably most of the time nothing, and every now and then I should see 1 point. And then I need to check one global thing, which is that there's no points that are really far away. So I need to check that everything is contained in some set. Because then what I'm saying is it's contained in some big set, then it's compact. And if it also looks like at most 1 point in every region, then it's discrete. And if it's compact and discrete, then it's a finite set. And so it uses the fact that I can talk about configurations of endpoints, not just in the complex numbers, but in any subset, in any open set. And that this sort of assignment is a sheaf. So if I want to give a configuration of points, I can give some points here, I can give some points there, and I can check that on the intersection I've given the same set of points. In fact, it's something a little better than that. It's what's called a homotopy sheaf, which means that if I want to give a configuration, I can give a configuration here, a configuration there, and on the intersection, I don't have to give the same configuration, but I should give a deformation of one of them to the other. And then I can make a global configuration. That's a stronger property somehow than being an actual sheaf. So the point is that this, when you take so-called global sections, you get the space you're interested in, configurations of arbitrary points, but it has a kind of local nature, and so you can expect to describe it using this local picture, which is just either I see 1 point or I see no points. So that's the general shape of the strategy. I don't want to say anything more precise about that. Now, the issue for using this strategy here, these coefficient systems, V lambda, they're local coefficient systems on the space of configurations, by definition. But they're not in any meaningful sense local on the complex numbers. If I want to know the value of one of these fibers, I have to know where all endpoints of the configuration are, so that I can make the branch cover so that I can take its first cohomology. So I can't determine by what it's going to be by looking at what happens in little small patches. I need to know where all points of the configuration are to calculate this abelian group. And it can't, yeah. So it's difficult to make that kind of thing interact with the first kind of thing. But there's a trick you can do, which is change the question a little bit. Let's look at the following. Let's look at configurations of endpoints in the plane and an x-valued function on the branch cover that they defined, where x is just some other space. This somehow is describable locally on the complex numbers. If I want to give such a thing, a configuration and a function from the branch cover it satisfies, well, locally, I give either no points or 1 point. If I give no points, then I have to give 2 functions, because the branch cover is not branched there. So I have to give 2 functions from that little patch to x. And if I see a point, then I have to give 1 function from that little patch to x. It's not really that little patch, it's the branch cover of that little patch. But this configurations with maps to x is somehow locally describable. And that means that this kind of first method applies perfectly well here. And you'll be able to calculate the cohomology of this object using exactly the first method. But the point is that now we didn't use anything about x. And in particular, everything is just functorial in x. So you can take this formula and you can take cohomology of this as one side, you can take whatever the calculation gives you as the other, and both sides are functorial in x. And then you can sort of, if they were like 2 functions of x, you could equate their Taylor coefficients. There's a way to do that called Goodwillie calculus in algebraic topology, which is thinking of things that are functors of a space. And so if you've got 2 things that give you the same function, then they must have the same coefficients. And when you extract coefficients, you discover you get exactly these twisted cohomology groups. There's a small bit of sort of algebraic manipulation you have to do. When you do this, what you get is it lets you calculate the cohomology of this space, conf n without the x, with many coefficient systems. And you have to check that you can find enough of them, that all the ones that you wanted to know are in there somehow. Because it will compute cohomology with not irreducible coefficient systems as coefficients, but some enormous sum of things. And you have to do some algebraic stuff that lets you split off the piece that you wanted. But let me just say that. So as I said, so they reduced this conjecture to showing that there are numbers a and b such that the cohomology of these configuration spaces with v lambda coefficients are independent of g in a regime that grows like a times g minus b. And the crucial thing is that you have to have the same a and b for all lambda. Because you don't really want to apply it to v lambda. You want to apply it to this thing, which was the exterior algebra of v to the rth tensor power. And that contains, roughly speaking, all v lambdas. If you want to prove a different thing, if you're happy for the constant to depend on lambda, then this is bread and butter stuff in this business of so-called homological stability. For example, this exact situation would fit into a paper I wrote a few years ago with Nathalie Wall, and it would just say, yes, the cohomology is independent of G for I less than G minus roughly half the size of the partition. But that is completely useless for this application, because when you want to do this over all lambdas, then the constant becomes minus infinity effectively, and so you've achieved nothing. So what they needed in order to finish this program was what we've ended up calling a uniform stability range, meaning a range that is uniform over all lambdas, or over, you get to pick some class of coefficient systems and it should be uniform over that whole class. So that's true. It turns out that one can prove that. I mean, what we can prove is probably not very optimal, but I less than 1/6 G minus 1 turns out to work. And if you take this and combine it with everything that they did, you get the following estimate. You get the left-hand side of the conjecture is the right-hand side of the conjecture plus big O of this thing here, where I think the 12 here is exactly 2 times the 6 there. And as long as Q is big compared to R, this will be little o of 1 with respect to G. So at this point, I have to emphasize that this does not answer the conjecture as they stated. The conjecture is for all Q and all R. So if you want to understand the distribution, then you need to understand all of its moments, which means you want to fix a Q and you want to know something for all R. but this shows that you get it for Q that are big compared to R. So this actually gives no actual case of the conjecture. So in other words, it does not determine the distribution, knowing these moments, but it determines the moments. So in the remaining time, I want to give one very vague idea of how we do this and what do we do that's different to these, for example, these earlier kinds of theorems that had lambda in the constant. It's going to be very vague. So we don't just prove this case, we give a different kind of strategy for proving this kind of theorem, this uniform stability kind of result. It applies, for example, to Modified surfaces, it applies probably to other things as well. And the point is, let me hide that for a second. The point is that this notion that you have uniform stability is sort of without precedent for most examples of groups that people study stability for. But there's a sort of example that you can think of as being a precedent, which is a theorem of Borel, which says the following. If I pick an arithmetic subgroup, for example, sp2g of the integers, and I pick a non-trivial irreducible representation of it, then the cohomology vanishes for I less than g, whatever lambda is. Now, if I have two cohomology groups which are both 0, then they're also isomorphic to each other. And so you can interpret this as saying, if I do this for sp2g and I do it for sp2g plus 2, the cohomology groups are the same because they're both 0. So that is kind of a precedent for this kind of result. It's much stronger, of course. I mean, knowing what the cohomology is always better than knowing how it behaves. But what we do is we make a strategy that lifts, when you have families of groups over an arithmetic group, it gives you some conditions you can check so that it will inherit this kind of property from the arithmetic group. So in this situation, it turns out I have to undo one of the simplifications I made in my talk, which is that it is very important to do all n. I said, let's take n to be 2g plus 1 for simplicity, so I don't have to deal with two cases of everything. For this strategy, it's very important to not do that and honestly do all n at once. So this Bureau representation always goes from the nth braid group to the n minus first symplectic group. I chose n to be odd, so that n minus 1 was even, so that nobody would say, what do you mean by the odd symplectic group? But here you have to say what you mean by the odd symplectic group. And it's not so complicated. You can take it, for example, to be the stabilizer of a unimodular vector in the next symplectic group up. But they're no longer arithmetic subgroups of sp2g something, because they will have infinite index typically. And so you have to prove something like this Borel theorem for these odd symplectic groups as well. But other than that, you can show that these even and odd symplectic groups satisfy the same conclusion as Borel's theorem. So now we're in a situation where we have, sorry, not the symplectic groups, these images of the braid group in the symplectic group, which will be an arithmetic group in the symplectic group. It's very similar, it's basically, it's like the level 2 congruent subgroup of the symplectic group, more or less, with a small variation. So these images do satisfy the same kind of conclusion, and then the strategy is to show the following. In undergraduate algebraic topology, the goal of everything is to calculate the homology of some example. And it's very nice for that to be the end result of whatever you're doing, is you've said the homology is something. But for all sorts of intermediate steps, it's a very good idea to not take homology until you really have to. And in particular here, instead of asking about the homology of these groups, we can take their chains and manipulate those for as long as possible until at some point we say, okay, now we'll take homology. So what we show is that you can construct the chains on these groups with coefficients in something in a precisely controlled way from all the chains on all the braid groups of smaller index on all the v mu's of smaller mu. So there's a recipe. It's not very explicit. It sort of says, in rough sense, it says there's a spectral sequence going from these to that, roughly, but it's a bit more precise than that. And what we do is that because the word precisely controlled means that if the braid groups didn't have stability in a uniform way, then some relative homology group of a braid group relative to a previous one would be not zero anymore. And that non-zeroness would propagate all the way through this business, and it would prove that these gamma ends also do not have stability. But they do, because of this theorem of Borel, or at least something very close to this theorem of Borel. So somehow here is sort of where I enter the story. And this is my last slide. But I think it's a kind of very nice and instructive example of this sort of strategy. So the steps in the previous work of Bergstrom, Diaconu, Peterson, and Westerland is, even though they are not naturally people from this school, all the methods they use are of this sort of homotopy theory flavor, sort of moved into their situation from analogous situations. Here we had to make up some fundamentally new piece of what you might call higher algebra or something, telling you how to build you build the totality of these groups from the totality of these groups in some sort of systematic way. Yeah, I mean, it was inspired by this particular application to number theory, but it turns out, as often is the case, to be a general method that you can apply to all sorts of other things as well. So yeah, these are the two papers that I talked about, and thank you for your attention.
Questions?
Can you say a little bit more about what precisely controlled way you construct the chain complex for the large thing?
Small ones, or does that get too hairy?
So, you can take all the classified spaces of all the braid groups combined into one object, and that has some kind of multiplication defined on it by the fact that you can put braids next to each other. You can also take these groups gamma n that I mentioned, these images of the bureau representation in the symplectic group, and there's a map, because by definition gamma n was a quotient of beta n. And these also have some kind of multiplication law given by roughly block sum of matrices. And it's a good idea to take seriously the idea that both things are just single algebraic objects, analogous to a ring. When you take chains on them, that becomes even more true, because then they have an addition defined as well as a multiplication. And the fundamental thing you need to calculate is you need to tensor that one over this one with the trivial object. Tensor means in a very derived way. And this will be done in a category of natural numbers graded things. And it has homotopy groups or homology groups, and you have to prove that they have a vanishing line. In other words, you have to prove that you can build S as an R module with some control about what kind of R module cells you use. Yes. And that's generally a very difficult question to do, and we give some techniques for checking that kind of property. And one thing is that if you know how to build them both absolutely, in terms of so-called E-infinity cells, then you can get a good estimate on how to build them relatively. So if you know you can build this with E-infinity cells with a certain vanishing line, and you can build that in its own right with a certain vanishing line, then you can get an estimate on this. And for the braid groups, that turns out to be very easy, because it's this is in fact a free E2 algebra on one generator. And for this, you have to do, that turns out to translate to some certain simplicial complexes being highly connected. And then you have to go and do some combinatorial work to prove that they're, like, use some like discrete Morse theory type arguments to show that those simplicial complexes are highly connected. I thought it more instructive to explain the story than the techniques.
Other questions?
Just to, I mean, this particular explanation, how does that fit in with, in some sense, yeah, the group completions, if you have the map of group completion, that's sort of trivial. Does that get reflected in this type of explanation?
I don't think so. I think this
So
is
it's
a different way.
completely
Yeah,
orthogonal
yeah.
somehow, those-
Somehow the point is that all these representations v lambda are defined here, but you can't extend them to the group completion. So you can't really make an argument about them from the group completion point of view.
When you do various sums of moments over all of MG, people have various theorems about such things. None of the theorems I know use much homotopy theory of a serious sort. Do you know something like that for MG?
Right, so there's a, let me tell you what the essential difficulty is, doing things like that, which is that in this Grundig-Lefschetz trace formula, there's some, you fix a given G, say, there's some cohomology that you know. So if you know the limiting cohomology and you know stability, that gives you access to the first, let's say, 1/2 G many cohomology groups. And if you're lucky, you can also work out how Frobenius acts there. And then that gives you the first few terms of the Grundig-Lefschetz trace formula. But now you also need to take the ordinary sum of Frobenius on all the remaining cohomology. And the way the eigenvalue estimate works is that the eigenvalues of Frobenius get smaller as you go up. But if the amount of cohomology gets bigger very quickly as you go up, then that will dominate the main term in the Grundig-Lefschetz trace formula. And the thing in MG is that we know there's an enormous amount of cohomology. There's super exponentially much cohomology. And so there's no way, and nobody knows what it means or anything like that. So there's no way of estimating how Frobenius would act on that stuff. And if it acted in a maximally sort of adversarial way, then it would just dominate everything that you knew. So another ingredient, in this case it turned out to be very modest, is that the amount of cohomology in the configuration space, there's an a priori estimate, which is there's at most 2 to the 2n. The total cohomology is a dimension at most 2 to the 2n, which is modest compared to other things.
For MG, there's not much you can get just out of topology.
I mean, I think that's very much not true. But in terms of counting points, yeah. I mean, there's all sorts of other difficulties as well, which is that it's not projective and so on, so you maybe don't know exactly what you mean by counting points, and you should maybe count an MG bar and things like that. But yeah, I mean, I think that's something that people do by other techniques, by literally counting points, in fact. And you can try to turn the story around. You can try to literally count points and then determine something about what the cohomology must be from those point counts. And I think on MG, maybe that's been the more successful direction.
So you use Borel's theorem in the case of the symplectic groups. I guess symplectic sort of comes from the form of the functional equation.
Symplectic comes from the fact that the intersection form of a surface is antisymmetric.
So are there examples where the other groups, like the orthogonal groups,
Yeah.
algebraic surfaces instead of curves?
I don't know. I think Dan Peterson, my co-author, has thought more about that. Yeah, I don't know. There are some properties of the symplectic groups which are incredibly convenient for making this work, which are not true for the indefinite orthogonal groups, for example. So there's something a bit special about the symplectic group.
Right. Well, let's thank Oscar once more. Fortunately for us, we're glad that Mike Hill, on very, very short notice, has been able to step in and replace Mustafa Fall. So Mike Hill is Ordway Professor in the School of Mathematics at the University of Minnesota. He was a speaker at the ICM in 2014 and received the Oswald Veblen Prize in Geometry in 2022. And he will speak on group actions, algebra up to homotopy, and flavors of commutativity.
Thank you, John. Yeah, thank you for the opportunity to speak and to share some things that I find really nice with you. Due to the short timeline, I'm going to put any problems that show up with my talk. That's going to be my excuse, and I'm going to be as surprised as many of you at what shows up on the slides. Kind of a fugue state. But this one, I like to start with this. These are pictures of the 17 wallpaper symmetry groups. And I found this amazing 1980s color paletted picture of the wallpaper symmetry groups. I know it's like incredible. online, and I use it when teaching a course on art and math to undergraduates. And this course tends to not draw math majors, but it tends to draw people who always start the class, and this is a really awkward way to start a math class, with, I don't like math. It's not me saying that, it's the students. It would have kind of a different vibe if I did it, and they'd probably have a lot of follow-up questions, but they always start with this. And I like to do this because my goal for this class, and actually my goal for this talk, is the ubiquity of group actions in things that might be fairly disparate. In this case, from their perspective, art or tile work, and from our perspective, things like smooth structures on spheres. And so to get into the actual content, I'll start with this question that I'm going to attribute to Milner for a lot of reasons that I'll get into, namely, how many smooth structures are there on the n-sphere? And you might think this is kind of a surprising question. And in fact, if you were a mathematician before the mid-50s, you would have assumed the answer was 1, because surfaces have a unique smooth structure. One manifold, so the circle, has a unique smooth structure. R to the n generically has a unique smooth structure. R4 doesn't. That's a whole thing. But the others, they have a unique smooth structure. And it was thought that spheres, because like they're not that far from Euclidean space, it's like 1 point away. How bad could it possibly be? And in the 1950s, Milner shocked the math community by showing that the 7-sphere has exotic smooth structures. There are smooth structures I can put on the 7-sphere that are not diffeomorphic to the standard 7-sphere. And so this led to the question of, well, how many do I possibly have? And one of the ways this started to be approached is actually through the Poincare conjecture, and to sort of lift the problem into a more homotopical one. And the original formulation of the Poincare conjecture, this is the topological one, where I can ask if I have a homotopy n-sphere, by which I mean I've got some manifold, and that manifold has a trivial fundamental group, and the homology groups of that manifold look like those of a sphere. It has a single non-trivial homology group, and it's in the dimension of the manifold. So if I'm in that situation, then I want to know, is it actually homeomorphic to the n-sphere? And if n is at least 5, then Smale showed this using the H-cobordism theorem. If n is 4, Friedman showed this using really complicated things. I already said R4 tends to be weirder. And then when n is 3, Perlman showed this, and that in fact it's always the case. And you can think of Milner's question, Milner's result, is that the smooth version of the Poincare conjecture is generically false, that I can have something that looks like the n-sphere, but it's not diffeomorphic to it. And so the way that, that we're going to approach this is to use work of Cavere and Milner, where they said, let's lift the problem from understanding the count of some set, namely the cardinality of the set of smooth structures, up to diffeomorphism on the n-sphere. Let's find a natural group structure for this and analyze that group. And what they showed is, well, first they show it's a group under connect sum, and I had to sort of bind my hands behind my back to speak more professionally and not gesticulate wildly. But now I get to, because you start with these are two spheres. Maybe they're exotic spheres, maybe they're standard spheres. I'm not going to judge them. And then I choose in each of them a little standardly embedded open disk, and I'm going to delete those open disks, and I'm going to build a bridge between them. So they look like the Death Star, if you're familiar with Star Wars. If you're not, I've got like such a surprise for you after the talk. It's called Star Wars. And what I do is I just smoothly connect the two of them. I really should have probably built a little collar on top of it, and then it just locks on. And this gives me a way to take two spheres, possibly with non-trivial smooth structures, and build a new one. Because if I just inflate that orange section like a balloon, then I'm going to end up, it's going to expand out more and more, and now I'm going to have something that looks like a standard sphere again. And what Cavere and Milner showed is that this group, theta n, of diffeomorphism classes of n spheres, can actually be connected to a different quantity, which I didn't provide any explanation of on this slide. I will tell you about it. Namely, the stable homotopy groups of spheres and a quotient of it. So here I have two concepts, one of which is purely in differential topology, namely smooth structures on spheres, and the other is firmly in the land of homotopy theory. Well, that's a little bit of a lie, because to define what I mean by the stable homotopy groups of spheres, I'm going to go backwards in time to the 1930s. And in fact, this is work of Pontryagin. This is shortly after the homotopy groups of spheres were defined by Čech, and then Hopf and Alexandrov said, you gave the wrong definition. He hadn't, but they kind of convinced him that he'd done it wrong, so he withdrew the paper. But Pontryagin ignored that and said, we're going to stick with your definition of the homotopy groups of spheres. And he showed that and I'll talk about some of these definitions later, but he showed that there's a dictionary that connects the homotopy groups of spheres to a different concept, namely manifolds together with a framing. And that's a choice of basis for the normal vectors at every point. So I'm taking my manifold, I'm embedding it in a big Euclidean space. So my manifold in this case is this surface of genus G with 5 boundary components. And I embed that in a big Euclidean space. And then at every point, there's the tangent bundle, which inherits from the tangent in Euclidean space. And I ask for the normal vector set, the orthogonal complement. And if I choose a basis for that continuously, that's my framing. And Pontryagin showed that to give myself a manifold embedded together with a choice of framing is the same data as giving myself a map between spheres. And the way the dictionary works, going from the left-hand side from my perspective, I guess the right-hand side from y'all's, over to the other is fairly straightforward. I have a map between spheres. Generically, maps between spheres are smooth, and I can pick a regular value for that. That's like, say, maybe the little blue point or the little orange point, or sorry, the little red point at the bottom. And then given my map between spheres, I can take the inverse image of that. If it's a regular value, that's going to be a manifold that's embedded in my ambient one, the bigger sphere. And as I said at the start, spheres are basically the same thing as Euclidean space. So I could have taken my manifold embedded in the big Euclidean space. That's kind of the same thing as a manifold embedded in S to the n plus k with a standard smooth structure. And then I'm just looking at the pre-image of a regular value. That gave me my embedded submanifold. So from the homotopy groups of spheres over to manifolds. The cobordism relation, which I just said is mod cobordism. Boardism here refers to they're the boundary of something, and the co is the usual prefix of together. So cobordant means the two manifolds together are the boundary of some other. And that's why I've color-coded it. I had the blue part, that's maybe I chose one regular value, the little blue dot. And then I could have chosen a different regular value, the little red dot. And I'm in a sphere, so I can choose a path that connects the blue dot to the red dot. And I can take the inverse image of that whole path. And that's now a manifold that's one dimension bigger, whose boundary is the inverse image of the blue dot together with the inverse image of the red dot. So different choices of points gave me cobordisms, or cobordant manifolds. And then the last piece, so I've defined most of what showed up on the previous slide. The last piece is, well, if my manifold was, I choose S to the k, and I embed it in Euclidean space, then I can ask, what are all the possible framings on S to the k? And that gives me, it's a manifold together with choice of framing. That's an element in the homotopy groups of spheres. And that's the way I'm going to define the image of J. So Kerber and Milner then use this to show, okay, well, this map from the theta n's, the thing we want, the diffeomorphism classes of smooth structures, is surjective in like almost all degrees. So if n's not congruent to 2 mod 4. And then if n is congruent to 2 mod 4, then it's maybe surjective. The possible failure for it to be surjective is at most a z mod 2. And that z mod 2, the map that's not named there, little phi n, that's what's called the Kerber invariant. It's the obstruction to surgery in the middle dimension. And it's saying, if I can do this, if this invariant is 0, then the framed manifold I had could be turned into a framed sphere. And that's sort of the whole idea. And in work with Hopkins and Ravenel, I showed that in fact, unless we're in dimensions 2, 6, 14, 30, 62, or maybe 126, that map's always 0, so it's always onto. And in fact, I'm like super excited to say, as an update, work of Lin, Wang, and Zhu showed that in fact there is a manifold of covariant invariant 1 in dimension 126. So the examples that we had, that was in fact now a complete list. So the way we showed this is to use unexplored structure in equivariant homotopy theory. And I like to get a chance to talk about this, both because it led me into the field of equivariant homotopy theory. That's not where I had sort of started thinking about homotopy theory. And then it also lets me tie in one of the programs going on here now, which is the equivariant homotopy theory in context. And so I get to talk about some of the themes there. And then what we used was this feature of equivariant commutative rings. Namely, they have a multiplication map, and the multiplication looks commutative. But if I had things that are equivariant, so they have a group action everywhere, then I get to choose how does that group action interact with the different tensor factors. Does it just leave them in the standard order, or do I start to move things around? And letting myself make the choice of the group acting by also permuting the tensor coordinates is sort of new structure that we can play around with. And so what I want to do at this point is sort of move out of this introductory period and into this more, let me sort of give a little more history. Let me talk a little bit more about how I can think about commutativity and associativity and twisted multiplications, and then I'll return to applications. All right, so back to history. I'm going to actually start with sort of work of Poincaré in the 19th century. Actually, Tiana made like a really nice reference yesterday that geometric, I'm sorry, blanking on the ability to speak, sorry, what? Thank you. Thank you. That is the word I was looking for. The geometric measure theory came out of the name of a book by the same thing. It's not the same here. Poincaré didn't call this algebraic topology or homotopy theory. He called it analysis situs, which is, of course, what I would use to describe it to students. If I wanted to have terrible teaching evaluations. But the whole idea for this is that I'm going to start with just understanding loops in my space. And for me, a loop is going to be a continuous map from the interval in that starts and ends at the same point. So it's like the intuitive thing. I'm not asking that it be injective. I'm not asking anything. I just ask that it start and end at the same point and be continuous. And I very carefully rendered several images. These are clearly not made by AI because they're like extra bad. But in both of these, I have, on the left-hand side, I have a torus, and I drew 2 loops on it. There's a blue meridional circle that goes around the sort of obvious central loop in the torus, and it's harder to see, but there's also a little red circle that loops around longitudinally. And then in the other case, I have the punctured plane, and I drew a loop that goes around, and this may be one that you would have seen in some like a complex analysis course as I'm trying to loop around and figure out integrals around a pole. The notion that I want to use to identify these is homotopy, and this is due to Camille Jordan in the middle of the 19th century, where it's just a deformation of my path from one to another. So if I have 2 loops, and since I insisted that the starting point and ending point of my loops be the same, then these are the same thing as maps from the circle in, where I just identify the 2 endpoints. And I ask now that I have a map from the circle in, the circle cross an interval in, and I want it to start, so I'm thinking of the second coordinate as some kind of time coordinate, as as Oscar described. And then I want to think of this as saying, it starts with gamma 0, it ends with gamma 1, and I'm also going to ask that the loops have the same starting and ending point, and my homotopy fix that. So on the set of all such things, and the set of homotopy classes of these, I have an addition. And the way I can define it, I drew two pictures. I've got my two loops, alpha and beta, so they start and end at the same point. And the right-hand one is the one that you've probably seen if you looked at anything with the fundamental group. I first run my loop beta at twice the speed on the interval 0 to 1/2. That ends at beta of 1, which was the starting point again. And then I run my loop alpha at twice the speed, from 1/2 to 1. And I can do this in a different way. I can describe this instead as take the circle, and I marked one of the points, I guess the point 1, when I think of it as in the complex plane, and take the circle and just crush a different point down to that base point. This gives me now 2 copies of the circle, glued together at that common point. And on the, say, top copy, I'll do beta, and on the bottom copy, I'll do alpha. And I'm getting the same thing by just the universal property of the quotient. But when I try to make good on the fact that I called this a group multiplication, I need to verify things like associativity of this operation. And in this case, the way I did it, how do I go backwards? There we go. The way I did it, I had to break my interval into 2 parts, and then I ran it on different speeds. Well, if I try to do that for associativity, then at the very top, I broke my interval into 2 parts. There's the part where I do beta times gamma. That's the left-hand part, the sort of purple and red. And then I also have the half where I did alpha. Whereas the other way I could have associated would have been a part for alpha times beta. That all has to take place in the same half interval. And then the other half interval got the part associated to gamma. So I'm running them at different speeds. And the key observation that I'm going to attribute to Poincaré is that I can actually fill in. I just sort of stretch out how fast I run each interval. And this happens uniformly in the paths, in that it's not actually taking place in the paths at all. It's taking place instead in a different space, namely the space of the ways I could break the interval into pieces, and I just move around where those pieces were. It's the exact same idea that Oscar was bringing up in the previous talk about sort of a configuration of spaces. I'm choosing where were those endpoints, and then I got to move those around. And once I moved them around, that told me how to provide a multiplication on these paths, and then the homotopy in that space gave me a universal one. Now, the key thing about the fundamental group compared to the others, and this is why Hopp and Alexandrov thought that Čech was wrong, is that the fundamental group is not abelian. And in fact, the worst thing is, if you choose a presentation of a group, then you can write down a space whose fundamental group has that presentation. And so this tells me that, of course, spaces are also like a formally undecidable problem to know the homeomorphism type, or even the homotopy type, because I can't actually tell groups apart just from presentation. I mean, unless I'm really lucky. So what we want to do instead is keep working just in homotopy, not try and do this classification, and focus on things like how can I understand, or how can I really make precise this idea of I want to do group structures, but also just up to homotopy. And then this is going to be the object I'll work with for the next bit of the talk. If I have a pointed space, so it's a space just together with some base point, as I've been using this whole time, then I'm going to let omega x be the loop space, so the space of all continuous maps in. And I'm giving it some awful topology that I don't care about. And now I'm going to describe a way to build for any such thing a different kind of multiplication, that this doesn't have a preferred multiplication. And in fact, in some sense, to say it has a multiplication is disingenuous. really what I get to say is, given any embedding of n copies of an interval into an interval, then I can write down a multiplication. So this is what I saw with associativity, and I'll just like jump back. Here I had two distinct ways to embed three intervals into one. I embedded them in as 0 to a quarter to a half to 1, and then I had 0 to a half to 3/4 to 1. But in both cases, it was, and in fact, if I looked at any horizontal slice as I moved my way along, it was an embedding of three intervals into one bigger one. So exactly this. And I drew a little picture and I tried to color code them, though it doesn't quite show up the way I might have liked. There's three intervals. This also took an embarrassingly long time to draw by hand. The three intervals are actually all the same length as the black interval at the bottom. And then I have a blue interval, a green interval in the middle, and then a red interval. And I had them embed in. The blue one embeds into that very first little blue spot. Oh, right, I have a light. Oh. I've got this little blue interval, a little smaller green interval, and then a little red interval. And associated to this, if I glue the two endpoints of my ambient interval together, then I've got a circle. And I want to think of these two endpoints here as being this point right here. And that's my circle wrapped around. Then I see that the embedded intervals inside it give me a little collection of embedded arcs that I've painted different colors. This one I painted blue, and then one that I painted green, and one that I painted red. And the complementary part to these little embedded arcs, they all are just like the original, the ambient sort of black color that I'd colored the entire circle. And I get a map from the circle to a bouquet of circles where I say take all of these little black, the complement to my embedding, take all of those points to this same crushed point. Crush it all down to one. And so given any sort of embedding of intervals into the bigger one, I've actually written down for you a map from the circle to a bouquet of circles. And the nice thing is, if I were to vary those embeddings of those three things around the interval, then that just sort of slides the embedded arcs in my circle around, and it gives me a way to continuously deform one of the multiplications to another. Now it's kind of weird that I'm saying I have a multiplication associated to this because this does not look like a multiplication. I mean, a multiplication normally is like a map from the set cross itself back to the set. This is a map from a space to a bouquet of copies of that space. But when I take continuous maps out of this, and I ask that they be continuous pointed maps out of this, to specify a continuous pointed map out of this, you just have to tell me a pointed map for this one, a pointed map for this one, and a pointed map for this one. So to specify a continuous pointed map out of this, it's a triple of continuous pointed maps. So maps out of this is the loop space cubed. Maps out of this was the loop space. And when I was doing maps out of it, there's a variant swap, so this gave me a map from the loop space cubed back to the loop space. And any choice of embedding of intervals gives me something like this. So again, I've parameterized all of the possible ways I could do this. This is due to Stashev. And I can do better because I could keep multiplying these, and I could embed intervals into my embedded intervals, and so on. And so in this case, the green was the same, the red was the same, they went in the same way. Then I put in a little gold and a little purple, and they got embedded into the original blue one, and then I further embedded. And if it looks, oh my god, I can't see anything, there's an itty-bitty gold one, there's an itty-bitty purple one, that's fine. It was actually by design that you wouldn't be able to see the thing. This is not just a happy accident. But the idea is that it doesn't matter. In this case, I have given two embeddings, an embedding of two intervals into one, that's this one, and then an embedding of, say, 1 into 1, that didn't do anything. Here, I was able to take all three of these and produce an embedding of 4 things into one. I'm not going to use the lightning. So this is parameterizing for me associativity of it, that as I continue to compose my way through, I should think of this as giving me a way to combine these. And lastly, I have an action of the symmetric group. If I just consider this space up to homotopy, it is really closely related to the configuration space that Oscar talked about. The key distinction between the two of these is I'm doing it just in the interval for now, and my configuration spaces are ordered. That the difference, the way the intervals go in, is essential part of the information, as opposed to modding out by. But it's the same, I don't know, same neighborhood. So Peter May took all of this data and he assembled it into a type of structure that we can consider. And he called it an operad. So it's just a sequence of spaces, just like my E sub 1s of n's. So 1 for each n. And I have these composition maps that are describing for me essentially certain kinds of like associativity and reorderings. And an operatic algebra is just a space together with a bunch of multiplications, and the multiplications are parameterized by the points in my operad. So it's just like I was doing with the embeddings of intervals into a bigger one. I want to think of that space describing for me all possible choices for the multiplication, and this literally just says do all of the multiplications parameterized by the space that parameterized multiplications. And the compatibility that I have is exactly that if I multiply and then multiply, that's something that should be already considered. And that's what the associativity at the top does. So I said that I have an E1. I actually have like an En for a general n, that I can embed things, not intervals into other intervals, but rather cubes, n-dimensional cubes, into bigger ones. And in this case, I drew a picture, and for me, I'm not going to distinguish between a cube and a circle or a sphere. And so here I actually drew the copy of two disks embedded into a bigger gray disk. I actually drew 24 disks embedded into 12 gray disks, and it's shaped like a clock, because I found an image of a clock on Tixi, and I was able to, like online, and I could perturb it. But then the idea that I want to do is actually all of the blue circles I'm going to view as a map from the two-dimensional disk into my space, and it's going to take the whole boundary of that two-dimensional disk to the same point. And in fact, all of the gray parts are going to the same point. The blue part is going to go in as one map, and I'm going to be using my right hand to indicate that. You're lucky I'm not making you also do these gestures as sort of a like, let's be kinesthetically active. Thank you, Björn. And the red map is going to be my left hand. And what I'm demonstrating with this clock picture is that the map that I get from the disk in, which crush the complement of these two disks to a point, is the same as the one where I just continuously deform as I rotate my hands around in the embedded two disk that's the plane between me and you to the other orientation. Here's where I started. Here's where I ended. This is commutativity of pi2 of a space. That I had one ordering that I was going to do, and Björn, I see you're doing exactly where I want to go with this, that here's one ordering of the multiplication, but because remember, any choice of embedding of two things gave me a multiplication, but any way I put my hands, I can pull them around into some sort of standard frame, and any two choices. The space of the embeddings of two disks into a bigger one is path connected. That's all I'm saying. But if I were to continue going around, I run into a problem. So the space of these is connected, it's not simply connected. And actually, the failure of simple connectivity is the failure of my arm to be able to pass through the other arm. That I'm witnessing painfully, I mean, for me, probably also for you, to watch it. I'm witnessing that I have a non-trivial monodromy as I go around. In fact, I could have done the same thing that wouldn't have given me commutativity. I could have tried to ask, why is the fundamental group not continuous, or commutative? And that's an easier case to do, but I also end up just sort of sliding my two embedded intervals. I can move them towards each other, but I can't push one hand through the other. Both because I'm not nearly strong enough, and then also that would be gross for all of us. And so this embedding of my hands into the interval is distinct from this embedding of my hands into the interval. One of these gave me the standard multiplication on the fundamental group, this one, because this is the preferred order for me of my hands. And then this one gives me the opposite multiplication for my group, and those are just different. I can't combine one to the other. If I allow the dimension of my cube to grow, though, we saw the difference between 1 and 2, the space E1 of 2 was not path connected, but E2 of 2 was. And as k grows, the spaces become more and more connected. So they become, it's not, the next one is simply connected, and then it continues on until you choose how connected you want it, and I can build one for you. And so if I pass to the limit, as n goes off to infinity, then this is something where I had a free sigma n action, and all of the spaces are infinitely connected. Infinitely connected spaces are contractible. Their homotopy type is a point. And so the homotopy types of these spaces in the E infinity operad is unique. It's the space that is contractible and has a free sigma n action. Any two spaces with these properties are the same. And since the homotopy type is a point, it tells me that I have an essentially unique multiplication. Remember, a multiplication is parameterized by a choice of point in there, but any two points are homotopic to each other. And any homotopies I would have between those are homotopic. It continues. I won't go too much farther down. So there's a unique multiplication. So there's the one that does it in the standard order, whatever that would mean. And then there's the one that does it in the other order, which let me rotate around. And I could keep going. And so I have something that's coherently commutative, it's coherently associative, all the things that I want. But coherence means, it doesn't mean that A times B equals B times A. It means that A times B and B times A are sort of 2 points in a contractible space. So they're essentially the same type of object. So at this point, late in my talk, I want to get to equivariant homotopy. And here I just want to talk about spaces with a group action, and then I'm going to redo the same thing. So here I have, my groups are all finite groups for simplicity. And then if you give me a finite group action on my space, then I have fixed points, which are what you think they are, just all the points fixed by whatever that subgroup is. And the fixed points is conjuvariantly functorial in the group inclusions. In my space of maps, well, I can actually endow this with a conjugation action, just like you see in, say, representation theory. If I have two representations, then the set of linear maps between them becomes its own representation with a conjugation action. And now I can use this to build variants of a loop space. So here, I'm just going to use the cyclic group of order 2, and I'll describe two spheres, one of which I'm going to call S1, and the other I'll call S sigma. And the diagram's actually color-coded, that the blue things are fixed by the group action. And then I'll also not rely on you being able to see that. This circle is entirely blue. The group acts trivially here. This circle is not entirely blue. There are two very large blue points. Those are the fixed points. And the rest of it is the same black that I've been using for all the text. And in the sign circle, this is the unit sphere in the complex numbers under complex conjugation. So the positive imaginary part and the negative imaginary part got swapped, but the real points were held fixed. These are two different actions I could put. On the left-hand side, the whole thing was held fixed. The right-hand side, only these 2 points are fixed. And associated with them, I have two kinds of loop spaces. I've got the continuous maps out of this one, where I remember that it had a trivial action, and then I have a signed loop space with maps out of it. So I want to play the same game that I did before. I want to say, okay, like Poincare did a pretty good job with the fundamental group. Like we've gotten a little bit of mileage from it. I'm just going to do the traditional trick in mathematics and borrow his idea. But I start to run into problems when I do this with the signed loop space. Absolutely nothing changes if I do this with the one where it was just the trivial action loop space. That one looks exactly the same and it works the same way. If I do the signed loop space, then what I have to do is I have to have my embedded intervals or embedded points in, but I need to keep track of the equivariance. So if I embed an interval in, I need to also have embedded its conjugate interval. Otherwise, when I try to do my crushing operation, the group action is incompatible with that. So for this, I want you to read this in two ways. I can read it to the right. So here's my sign circle in the middle. And then I've also adorned two little points that I drew with purple crosses. And my two maps are, well, the one that goes this way, just crush the two blue points together. And that gives me a map from the sign sphere to two copies of a trivial sphere, but now the group action took the top circle and it flipped it down to the bottom circle, and vice versa. So that's not just two copies, it's two copies of the one sphere, but it's not with a trivial action, it's swapped. On the other hand, I could have said, take these and crush those two purple points down to the blue point. And now I see the same thing, that two copies of the one sphere, and it's now glued to a copy of the sign sphere. So together, the left-hand map gave me a map from the sign sphere crossed, the loop space crossed with itself, where I swapped the two coordinates back to the signed loop space. And the right-hand map gave me a map from the loop space cross itself back to the loop space. I don't have a multiplication, though. I only have these sort of twisted versions, where the twist, in this case, comes from the fact that I sort of indicated down here, that one, that I'm swapping these two coordinates, and that's how the group is acting. Now, I don't know. In the interest of time, I'm going to skip spelling out all the structure because I actually already wrote it on the previous slide. I had those two kinds of multiplications. This just unpacks it. So what we can do more generally is ask for a generic twisted multiplication, where instead of having maps from x cross the n back to x, I can now let the group act both on x and on the set. And so a particular example of this is choose an identification between my set of 1 to n with the cosets of some subgroup. And so I get that that set is now G mod H, and I'm looking at maps from G mod H into X. And if I had a twisted multiplication, then I'm going to call this a norm. Now this is something you've probably seen from Galois theory, and that's where that name is coming from. If I have a Galois field extension with Galois group G, then the group is acting on the bigger field, and we have two ways to take ourselves from the bigger field back to the smaller one. The smaller one, which is the fixed points, includes in, but then I can additively go back, where I sum over all of the elements of the Galois group, or I can multiplicatively go back, where I multiply over all elements of the Galois group. When I think of how is the group acting on either my sum or my product, the group was acting by permuting the terms that showed up in the sum, or it permuted the terms that showed up in the product. So this transfer, or trace, is the way it's normally called in Galois theory, and then the multiplicative norm are exactly describing these kinds of twisted operations that I wanted. Okay. So if I want to play the same game as before for describing coherently commutative multiplications, Andrew Blumberg and I defined a collection of operands that did this, where I'm going to still want to have the symmetric group acting freely, and then I want the spaces to essentially have that same property of their unique homotopy types. They're contractible. And then I also want to have a multiplication. And so what I want to get to is just sort of this sort of feature. I can associate to these conditions combinatorial data. Namely, if I have a subgroup that of the group G cross sigma n, that's what was acting on the spaces of my operad, and it intersected sigma n trivially, then this kind of subgroup data is the same data as a subgroup H of G and an H set structure on the set from 1 to n. So the kinds of groups that I said I want to consider here in this point 2, point 1 says any subgroup that has a fixed points that are non-empty had to intersect sigma n trivially because of the freeness. And then I'm asking what kinds of subgroups show up. And they correspond to H sets of various cardinalities. And the amazing result, and I'll sort of, here we go. The amazing thing is that this assignment tells me everything. If I start with some way to look at these operands that describe not just a coherent multiplication, that's what the last condition did, but a coherent multiplication and coherent norm maps, then the data of that is the same data as a combinatorial object, namely these choices of H sets for various subgroups H. Andrew and I were able to show that we had the fully faithful embedding of it, and then a group of earlier career mathematicians were able to show that, in fact, I could realize all of them. So I actually don't remember how long I'm supposed to go for, but it's giving me increasingly angry colors. So I'm going to stop here. Thank you.
Questions for Mike?
Applications?
I couldn't have planted you better. This was our big one. So how did I started with differential topology. And then I want to now, thank you, return to differential topology. How did we actually show it? We built a cohomology theory that would detect any of the manifolds that had covariant 1. And then to build this cohomology theory, we used these kinds of twisted multiplications. We sort of universally built one that came from manifolds that look like the complex points of a real algebraic variety. And then we built that up to work for a larger group. And then showing all the things that we needed, namely showing it had periodic homotopy groups, showing that it had zeros in its homotopy, that was the same thing as just sort of unpacking what happened with these various twisted operations. So, thank you. Oh no, the Star Wars surprise was that there's an incredible movie series called Star Wars. And you can watch it on Disney+. I don't know if actually referencing the Disney franchise means this will be taken down from YouTube immediately, but I mean, if I started singing any of the theme songs, it would be. And but so if you haven't seen Star Wars, like, we'll watch afterwards. It would be great. That's the surprise.
No further questions? Thank you very much for a wonderful